Good morning and welcome to MiniLecture 6. In this lecture, we're going to talk about making new functions from old functions. So we're going to talk about different ways of transforming the functions that you've learned about in the past couple of lectures, like polynomials or logs or exponentials, and how to make them more complicated by combining them together and moving them around in the xy plane. All right, so let's get started. First, let's just do a quick review of the functions that we've talked about before. So the first of these was a polynomial. So for example, a polynomial is of any function of the form g of t is equal to a0 plus a1t plus a2t squared plus all the way up to some degree n an t to the n. So one specific example of this is where all of the constants are 0, so all the a's are 0 except for a2, and so you have a simple quadratic f of x equals x squared. All right, so that's a function that you've already learned about. And you've already learned about the natural log of x, or the log of x, but you could actually combine the two and get something like f1 of x is equal to the natural log of x squared. How do we make this new function, the natural log of x squared, from the old functions that we already have? Some other new functions that we can make, for example, from e to the x, is e to the 3x, or 2e to the 3x. Similarly, we could go from starting with log of x, or some logarithm of x, and have minus log of x plus 3. This is a function that is kind of polynomial-like in that it has these two terms, but it has a logarithm. So how do we create that? All right. So the first thing that we might want to do is we might want to move a function up and down or left and right in the xy plane. So you could start with, for example, a simple quadratic polynomial like the blue curve here, and you might want to move it up or down to create the red or the green curves. So if you want to move it up, the value of y that you had before, you want to add to that y. So you have your old function and you add some quantity a to it, so plus a. So for example, from our old function, if the blue is f of x, we could create f1 of x by having f of x plus 5, or we could shift it down 5 units by having f2 of x is equal to f of x minus 5. So this is f of x plus 5 and minus 5. So how do we know that we're adding 5 here? Well, this point that is at the y-intercept, so it's also the x-intercept here too, but let's focus on the fact that it's the y-intercept, shifts up to a new y-intercept that is at 5, or it can be shifted down to a new y-intercept that's at minus 5. All right. So second, we can move a function to the left or to the right on the axis. And so we can do this by, instead of adding on the outside of the function, we change the value of x. So instead of plugging in x, we plug in x plus 2 or x minus 2, or in general, x plus a or x minus a. All right, so if this is our function f of x, then we might want to shift it to the left 2 units. So we're going from where this used to be 0, the root of the line, and we're going to shift that root of the line over 2 units to right here, and we're going to shift it over by adding 2 to it. And similarly, we can shift it to the right by subtracting 2 units of x, so you get f of x minus 2. All right, so how do I know whether I add 2 or subtract 2? That's going to be a sticking point, I think, for all of us, is whether we add 2 inside of this argument or we subtract 2. So the way that I think about it is thinking, what x creates the value of 2? So if I have my new function, this green function over here, I want x equals 2 to map to the old value of 0. So what is the new 2 used to be the same as 0. So we have 2 plus some unknown quantity a is equal to 0. Now, what value of a do I have to put in here to get this equation to work out? Oh, I have to put in a equals minus 2. And hence, to get the green function, I do x minus 2 from the old function. So ask yourself, what value of x maps to x equals 0 in the old function? So this is the new old. And if you ask that question, then you can figure out whether it's a plus 2 or a minus 2. All right, so you can do more things than just shifting the curve around on the xy plane. We can also rotate it about the different axes, and these are called the x rotation and the y-axis rotation. So we could flip, for example, the log of x. So if we have f of x is equal to the log of x, then we could get f1 of x is equal to minus log of x. And that would take our curve and flip it across the x-axis as if the x-axis is a mirror. All right. Similarly, we can rotate functions about the y-axis. So we could start with our old function of f of x. Oops, wrong color. Equals e to the x, and we could rotate that about the y-axis and get f1 of x is equal to, now just like when we shifted up and down versus left and right, and we put the minus on the outside to change the y, if we want to change to move it up and down, we want to take the minus sign and put it on the inside here. So what used to map to a 1 now maps to a minus 1. So you want to change all the x values and change their sign. Okay, so we would get f1 is equal to f of minus x, which is equal to e to the minus x. All right, so we can combine these two and flip it not only around the y-axis, but around the x-axis to get the red curve by rotating both of these. So the red curve is minus f1 of x, which is equal to, because we just switched around the x-axis, and then we want to switch it around the y-axis, so we have that this is equal to minus f of minus x, which gives us minus e to the minus x, which is that red curve that you see there. All right, so those are the ways to move curves around the xy axis and to rotate them about those axes. But we can also scale the axes, so this is like stretching the y-axis or stretching the x-axis. So first we could start to stretch or shrink the y-axis by multiplying on the outside of the function. So if we want to take this blue curve, f of x, and turn it into the green curve, we're essentially stretching that x-axis by 2. So we're stretching out all the points. So the point that we had here now maps to twice that value. And the point that we had here, now this is 2 up, this is now 4 up. So you're stretching that y-axis. All right, so to do that, we get f1 of x is the old function f of x multiplied by 2. So for every y value, you just want to double that y value. So you get your y value, and then you double it. All right. Similarly, we can multiply on the inside of the argument to stretch the x-axis. So if we have our curve f of x here, and we want to stretch it to get this red curve, what we can do is what used to be 2 here is now x equals 4. So we're going to multiply on the inside. So we have f1 of x is equal to f of 2x. All right. So those are all the different ways of stretching and flipping and moving curves around the xy plane. But we have one more thing at our disposal, and that is called a composite function. So a composite function is a way of combining two functions. So what we're going to do is we're going to sequentially plug the independent variable into one function, and then we're going to take that whole thing and we're going to act like it's a new independent variable and plug it into a second function. So for example, let's consider two of the functions that you guys are already familiar with, the log of x and x cubed. So this is a cubic and this is a log, and we can combine them in a composite function, and we write this with really interesting notation where we write it as f and g, f with a little circle, and then g of x. And how you read this is f of g of x. I think the reason I'm stumbling here is I think this word should say of. So it's f of g of x. Okay? And if we take that composite, oh, actually, never mind, ignore me. Okay, but the way that we read this is f of g of x. So you're going to first plug that x value into g, and then you're going to plug the whole g of x into f. So we do this in two steps. We first evaluate the inside function, so we get g of x, and this is simply plugging x into g of x, and this is simply the cubic that we had before. Now we want to evaluate the outside function. So we're taking f and we're plugging the whole g of x in for what used to be x in that function. So we have this is equal to the log. Now, wherever we had x before in f of x, we're now going to plug in the whole g of x, which is x cubed. All right. And I would like to note that the order of the composite function here matters. So f of g of x does not equal g of f of x. So if we plug x into g and then g of x into f, this does not give us the same thing as plugging x into f and then f of x into g. And so if we were to plug things in the opposite order, instead of getting log of x cubed, we would get log of x, which is our f of x, and we would plug that into our cubic, and we would get log of x cubed. Now, note that this notation of log of x cubed is not really particularly convenient. It kind of gets annoying to write all those parentheses, and it would be confusing to write log of x cubed, because it's easy to accidentally think that you're cubing the x here, the argument, and not cubing the log of x. So when we write the log of x cubed, instead of writing that little 3 over here by the argument, we actually move it over to be by the log, just so we don't accidentally end up cubing the argument. So don't do this. Down here, instead, if you don't want to write the parentheses, you have to move that 3 over here, so it's log cubed of x. All right, so that's a composite function, and with that I'm going to leave you with this self-study problem where you get to try to create different curves using these transformations and composite functions.